Hi everyone. In this video I want to relatively briefly go over the separation scheme of benzoic acid, benzocaine, and biphenyl. This is exactly the same as the first liquid extraction that you did. You started it the first day, and then the second day you finished it, or liquid/acid base extraction. So what you have to do here is kind of develop a separation scheme to separate these three molecules. And if you look back at that experiment, you can find that those things have been made available as a previous video, but I do want to go through it quickly here. So here we have a list of the reagents available, and then we have regular techniques like extraction and things like this. We can evaporate and things like this. So the first thing I want to do is I want to go through this list and knock off things that we may not use. So 10% aqueous NaOH, an aqueous base, that's possible. We have 5% aqueous sodium bicarbonate, that's possible. We have 6 molar HCl, which is an aqueous acid, that's possible. 5% HCl, another aqueous acid, that's possible. Diethyl ether, a common organic solvent, that's possible. Methanol, you're probably not going to use. Why not? Because it's miscible with both water and organic solvents, at least some organic solvents, so we're probably going to skip that. Lithium aluminum hydride is a reducing agent, we're not going to use that. Water, we might use water. Phosphoric acid, we're not going to use that. Sodium and magnesium sulfate are both drying agents, and you could use them interchangeably for the most part, at least in this course. But we usually use sodium sulfate, so I'm going to eliminate magnesium sulfate. It's not wrong to use magnesium sulfate. CH3COOH is acetic acid found in vinegar. We don't really use that for liquid extraction. And then finally, sodium borohydride, another reducing agent. So if you look here, there's like half of the things, and we can't use them. So when you're taking your quiz, you might quickly go through the list and just knock off the things that are not going to be used. All right, so when we start here, we're going to start with our benzoic acid, our benzocaine, and our biphenyl. Whoops. And what we want to first do is extract them out of ether. So dissolve in ether and extract with, in this case, I'm going to get rid of the benzoic acid first, so I'm going to extract with the base first, which is 5% NaHCO3. Well, what happens when you add NaHCO3? Sorry, I didn't mean to chop that off there, but that's what we're going to do. Well, what happens is when we add 5% NaHCO3, if we have benzoic acid dissolved in ether plus NaHCO3, which is aqueous, we're going to pull off this acidic proton. This is a carboxylic acid, and this is the acidic proton, and we're going to pull that off. And when we do that, we get this molecule, which is called sodium benzoate. And then you'd get H2CO3, but H2CO3 isn't stable, so it breaks up into H2O liquid plus CO2 gas. The million-dollar question is, what is the state of matter of this sodium benzoate? Well, the sodium benzoate is an ionic compound, so it's not soluble at all in ether. So it is going to be aqueous. So you've now removed the benzoic acid and as sodium benzoate, drawn it into the aqueous layer. So moving back to our separation scheme, on the aqueous layer, we're going to have sodium benzoate. And then on your organic layer, we're going to have benzocaine, biphenyl, and traces of water, because now we've basically added a liquid extraction. And then if you want, I think it's optional, I'm going to put ether over here, because organic layer implies that there's ether. Now when we get our sodium benzoate, what else is going to be there? Water you could put there, okay, and possibly CO2 gas bubbling out. Now what do you want to do? Well, I want to focus on isolating my sodium benzoate. So what I'm going to do is just hold this, so hopefully we can see everything on the screen at the same time. Nope, we can't. All right, so I'm going to have to move this back on and off the screen. So if I want to get my sodium benzoate back, and I have this molecule in the aqueous layer, well, how am I going to get this back? I need to add an acid and reprotonate it. So in this case, I want to add 6 molar HCl, because 6 molar HCl is one of my acid choices, and I apologize that I can't fit all this on the screen. You're going to end up with a solid and an aqueous layer. Well, what happens? So I have this molecule in solution, and I add HCl aqueous. This proton reprotonates, and what I get back is my benzoic acid. But this is in water solution. So in water solution, this is not soluble, so this is a solid. And my byproduct is just my Na plus and my Cl minus, or NaCl aqueous. So this is basically what's happening. In the first step, we're getting this molecule to form sodium benzoate, and then in the second step, we're reforming the benzoic acid. Essentially, we're driving this reaction in the opposite direction by adding HCl. So in this case, my solid is benzoic acid, and my aqueous is NaCl. I should also put that after I add the 6 molar NaCl, I'm going to have to filter out my solid product. Okay, because I do get a solid here. All right, now let's look at the benzocaine. In the case of benzocaine, I need to do the opposite. I want to, in this case, add an acid in order to protonate the benzocaine. Well, what do I have? I have 5% HCl. One thing I will notice is that we have 6 molar, we have 5%. We're not going to be super picky about whether you have the right concentration. Generally speaking, we want to use the lower concentration of the HCl here because there is more molecules in solution. Here we want to use a higher concentration because we just added a bunch of base, sodium bicarbonate, and we need to neutralize that base before we can protonate our sodium benzoate to make benzoic acid. But that's a technical detail that you don't have to be super familiar with. What are we going to get? We're going to get an aqueous layer, and we're going to get an organic layer. Okay, so what's going to happen? Well, in this case, we have benzocaine. And benzocaine looks like this, and it's dissolved in ether. And we add HCl, which is aqueous. So what we need to think about is, where's the most acidic atom on this molecule? Well, this is nitrogen. This nitrogen is going to grab this proton. And what you end up with is NH3 with a plus charge. And this just goes along for the ride. The ester group just goes along for the ride. Whoops. Like that. And now we have this protonated molecule, with the Cl minus being the counter ion. This is ionic again, just like the benzoic acid case. So this is now aqueous. So we've now made this into the ionic salt. We can call this benzocaine HCl. Okay, so benzocaine hydrochloride forms when we add the HCl. Everything else just goes along for the ride. We have biphenyl. We have trace water, and we have ether. Now we want to get this benzocaine HCl back as a solid. Well, we need to add a base. What do we have? We have a stronger base, which is 10% NaOH. So we're going to add 10% NaOH, and then it's going to precipitate, so we're going to have to filter it. We're going to end up with a solid and an aqueous. What happens when we add NaOH? So we add NaOH aqueous. What happens? This OH grabs the proton, and we go back to our original benzocaine molecule. This benzocaine is not soluble in water, so it precipitates out as a solid. And then we end up with H and OH, which gives us water as a liquid, which is just more water, and NaCl, which is aqueous. So this is basically what happens. Now, to draw the separation scheme, you don't need to know these reactions. However, on the final exam, there's several questions about these types of acid-base reactions, which again, you can find in the liquid-liquid extraction experiment, which I believe is experiment 3. So in this case, we get the solid, which is benzocaine, and our aqueous is just NaCl. Now, we want to get rid of, or get our biphenyl back. How are we going to do that? Oops, we need to do that. Well, first thing we got to do is get rid of the trace water, and that's what we can use our anhydrous sodium sulfate for. So we're going to add anhydrous, Na2SO4, and we're going to decant that, which just means pour off the liquid. So what we end up with is a solid of Na2SO4 coordinated to some number of water molecules, and our organic layer is going to be our biphenyl and our ether, and then we can either distill or evaporate ether using the solvent evaporator. It's basically the same thing. So we're going to evaporate the ether, and our gas, I guess, will be our ether after we've dried it, and our solid, or it may have been a liquid at first, but it will eventually be a solid at room temperature, is our biphenyl. So this separation scheme is exactly what we did in the course. And what I'm going to do is just stop this for 1 second and move the camera a little bit so we can see the whole thing. So this separation scheme shows us everything that's going on in the whole, in the entire separation. And you'll notice that along the way, it not only has all of the molecules, but it has, like, we decanted, we filtered, we extracted, and things like this. So it just gives us kind of everything that you're doing and how the reaction is going. On the quiz, again, make sure you get rid of anything that you don't actually need. And also, these reactions, although not important for this quiz necessarily, I mean, they are because they're the driving force of what's going on, but they're not directly asked there. These reactions are very important for the final exam. So that's basically that. I wanted to make a relatively short video so that hopefully you were able to watch the whole thing. I appreciate you watching, and I hope this helps you for the third quiz.